This is the third video in a series of videos about buffers. In the last video, we did a truly awful example that took 3 entire pages to find the pH of a buffer system by itself, with a strong acid disturbance and with a strong base disturbance. And I don't know about you, but I never wish to go through that level of math again. And so thankfully, in this video, we're going to introduce the Henderson-Hasselbalch equation, which is going to allow us to skip that ice table in some cases. Okay, so what we saw when we did that last calculation, when we solve ice tables with buffers, after we do our ice table, we put those numbers into a Ka expression. So our Ka expression looked like this. For a weak acid, products over reactants, it always looks like H3O plus times A minus over HA. And we solved that, and there was quadratic involved sometimes, but we could save ourselves some work with the assumption, and now we're going to take our assumption one step further. So you may have noticed when we use that assumption in all of the problems we've done in the entire buffer video series, that assumption was always highly effective. It was always a success. Our error was always less than 5%. And it turns out that's part of the definition of a buffer, is that X is always going to be much smaller than that initial value for HA. So we noticed, or rather these guys noticed that this assumption will always be true for a buffer. And thanks to that, we don't even have to pretend to put the X into these two terms. We'll just skip it altogether. And if we can skip it altogether, we only have one X unknown, and that is this number. There's only an X right here. And if there's only one X, then we can feel free to manipulate that reaction to make it easier to use. So we can use our P function that we use to make pH and pKa to save time. So here's how this works. We're going to use the P function, which remember is taking the negative log of things. So we're going to take the negative log of this side, and we're going to take the negative log of this side. So when we do that, we get negative log of Ka, and this is a product, so we're going to say it's the product of this piece and of this fraction. We're going to separate them. Negative log of H3O plus, and when you multiply things and you take the log of them, you add them together when you separate them with a log. That's just how math works. Okay, so now we have this kind of sloppy looking equation full of logs, but remember that we named some of these things. The last time we used the P function, we named this pKa. We named this one pH. And we don't have a name for this one, so we're just going to keep that here. Beautiful. Okay, so let's see. This was our P function. Here we renamed stuff. Now we're going to rearrange it because I'm usually going to use this equation to solve for pH. So I'm going to put pH on a side by itself. I'm going to move this term over to the left. So pH equals pKa plus the log of this fraction. Conjugate base over conjugate acid. And both of these, we are assuming initial numbers, since we assumed that X was smaller than the initial numbers. And this, my friends, is the Henderson-Hasselbalch equation, your new favorite tool for buffers. So there are two conditions that we have to promise to apply or to abide by if we're going to use this tool. Condition number one, we can only use this equation to skip ice tables for buffers only. So don't go thinking you're never going to have to do an ice table again in your young life, because it's simply not true. This is not a catch-all. We can only use it when we're doing buffer problems. And remember, we defined when something was a buffer by saying that ratio is less than 10 and greater than 1/10. And check it out. This equation is part of the Henderson-Hasselbalch, so you don't even have to go looking for it. You'll have to find it to use the equation anyway. So if this ratio of concentrations is between 1/10 and 10, it's a legal move. You can skip the ice table. The other condition is that X must be small. So use it only when those two concentrations for the conjugate acid-base pair in your buffer are more than 100 times greater than your Ka, i.e., when X is much smaller than initial concentration of HA, or A minus, whichever you're using. So these are your two conditions. If you would like to use the magical tool that saves you a bunch of work, you have to promise that you really do have a buffer solution that isn't broken and that the change is really, really small. So let's revisit that awful, horrible problem that we spent 15 minutes doing in the last video. I will show you how much faster it will go when we use our tool, the Henderson-Hasselbalch equation. So here is that exact same problem again. We've got a buffer with 0.25 molar of the weak acid, 0.56 molar of the weak base. We want to see what happens when we add some strong acid and some strong base to it. So we still have to verify that we have a buffer with our conjugate base over conjugate acid ratio. Oops. 2.24, and 2.24 is greater than 1/10 and less than 10. So this is a buffer. So we are good to go. We have to find our initial pH, which is with HA and A minus only. So can we use Henderson-Hasselbalch for this case? The answer is yes. Oh no, where did that page go? There we are. So we said we have to have a buffer system where this fraction is between 1/10 and 10, and that is true. And we don't even have an X because there hasn't been a change yet. So X is equal to 0, so it's definitely smaller than the weak acid concentration. So we are cleared to use Henderson-Hasselbalch. So here it is, pH equals pKa plus log of initial weak base over initial weak acid. So we're looking for the pH. We need to know that. pKa. Now we don't have pKa, but we do have the Ka, and we know how to find it. You know pKa equals the negative log of the Ka, which is 1.8 10 to the negative fifth. Calculator says 4.74. We can plug that in. pH equals 4.74. Oh no. We might not finish it if my pen dies in the middle of the problem. Ugh. Just one too many acid-base videos, I guess. pH equals 4.74 plus the log of that weak acid concentration, 0.560 over the weak base concentration over the weak acid concentration, 0.25. Beautiful. Okay, plug it in. Calculator says 5.09 for the initial pH. Look at that, we're already doing better. Look at how much space it took me to do it on the last page. It took me like this much space. It only took me this much space. Doing great. Let's go ahead and move on to part A. 0.0060 moles of HCl added. How does that change the pH? We know that when we add a strong acid to a buffer, we're going to neutralize it with our weak base. And when we have a weak base and neutralizing, we need to do a DNA table, and DNA tables need to be in moles. We're going to just plug ahead because we already found the moles in a previous video. We're going to use our weak base. We're going to neutralize a strong acid. We're going to fully go to conjugate acid and water. DNA table. Squiggle. Okay, I'm going to steal these numbers from the previous time that we calculated the problem. Let me see. We said that we had, here's our last one, 0.075 moles of HA. And 0.168 moles of A minus. I know I'm skipping that work, but think of the pen. It died to make this video possible for you. And for our strong acid, the problem said we added 0.0060 moles of that. So D is for to stir with strong acid, N is for neutralize the strong acid all the way to 0 if possible. We'll subtract it from our reactants and add it to our products. Math happens here. 0.162, 0.081. Congratulations, you neutralized all of your strong acid. You are left with a buffer system of weak acid and weak base. Now, the next thing that we would do is an ice table. So can we skip and use our Henderson-Hasselbalch instead of an ice table? Do we have a buffer? Yes. And is X very small? Yes. So let's do it. pH equals pKa plus log A minus over HA. All right, so we've got pH, our pKa is a constant for this compound, 4.74 plus log. We need to have the molarities. We only have moles, but I'm going to do a trick, and that is that my number of moles divided by my volume can just be stuck into this equation to save some space. And when I do that, I can see that since the volume is the same, and I'm taking the ratio of these two, I can just cancel them. I don't even need to put the volumes into the Henderson-Hasselbalch. You can just stick the moles straight into the formula. Math happens here, and we should end up with the same number as before. 5.04 is the pH for the acid. Our original number was 5.09, so our change in pH equals negative 0.05. Beautiful. That was so much less work. Here's the last time I did this problem. It took up an entire page of paper. It only took up half this time. Beautiful. We are not going to do part B because my hand is getting tired. But there's a similar process. You still have to do the DNA table to neutralize the strong piece, but once you get to the buffer ice table, you can use Henderson-Hasselbalch to get to the pH faster. This has been so many videos and one entire pen ink's worth of buffers. The next set of videos will be about titrations.